Pleasure to be back. So this is joint work with Tim Roughgarden, and kind of the high-level motivation for this work is trying to understand the role that interaction plays in distributed economic scenarios. And the kind of the general observation here, which is not new, it was pointed out several times in the past, is that economic scenarios, most of economic scenarios we're familiar with, such as auctions, market design for resource allocation, and so forth, are inherently distributed because the inputs, the valuation profiles of the players are assumed to be private. This is the typical situation. And therefore, at least in some sense, economic scenarios are a classical fit to studying economic scenarios. And this point of view gives rise to distributed welfare maximization questions and distributed market design or distributed signaling problems. And today's talk will be related to the problem of decentralized equilibrium computation. And it has to do with this, well-known economic dogma that, every market eventually converges to equilibrium. And the question is, can we actually place some quantitative, can we quantitatively analyze the rate of convergence of such process? Can we place computational bounds on how quickly is this stability achieved? And the simplest setup in which one could ask this question is the setting of k-player games or even two-player games, which is the absolutely simplest strategic scenario one can imagine. So a two-player game is just a game like rock, paper, scissors, or a two-bidder auction on eBay. In this game, we are two protagonists, Alice and Bob, are playing a game. Each of them has a set of n possible pure actions, so to speak. So, for example, rock, paper, and scissors. And each of them has a payoff matrix specifying each player's outcome for any fixed joint strategy profile. So, for example, if Alice chooses to play scissors and Bob chooses a rock, then Alice is the loser because the rock wins, and Bob, in this case, will get a payoff of 1. I just want to stress that we will not be focusing on zero-sum games. This is just for simplicity. So this is just for the illustration purposes. And in the actual game, we allow the players to choose to randomize their strategies. So they're allowed to choose pure actions from some distribution on strategies. In this case, we say that the players can play mixed strategies. And in this case, the payoffs are what you would expect them to be. They're just the expected payoffs under this joint strategy profiles, under the mixed strategy profile of the expected. These are just the expected payoffs of each player's payoff function under this joint strategy. Make sense? So what captures the notion of stability in such games? And the most widely acclaimed solution concept is that of a Nash equilibrium. So we say that a pair of mixed strategies, mu and sigma, form a Nash equilibrium if, intuitively speaking, no player has any incentive to defect from the current strategy, assuming that the opponent adheres to his own prescribed strategy. So in this case, we require that, assuming that Bob sticks to his prescribed strategy sigma, Alice cannot improve her expected payoff by defecting to some other strategy mu prime. Make sense? So in this case, we say that mu is a best response strategy to the strategy sigma, and the same requirement holds for Bob. Assuming Alice sticks to her strategy mu, Bob cannot improve his payoff by defecting to some other strategy sigma prime. So far, so good. And the Nobel Prize-winning theorem of Nash is that any k-player, two-player game with finite strategies has at least one mixed Nash equilibrium. And perhaps surprisingly, the proof is geometric and has to do with, it's proved via Brouwer's fixed point theorem, which informally states that any continuous function from a closed disk to itself has at least one fixed point. So it has a point which is left intact under this mapping. So at this point, this is just a fun fact for the audience, but try to keep this in mind because this will be kind of the central object. We'll get back to this problem.
And the original proof did not use Brouwer, was more complicated.
Using, Kakutani's fixed point, right. So, but I think the modern proof uses Brouwer. And okay, so fine. So Nash proved that there always exists a mixed Nash equilibrium. And by the way, so the emphasis on the word mixed is crucial, right? It's easy to see that rock, paper, scissors does not have any pure Nash equilibrium. So there is no pair of pure strategies, say rock and paper, that form a Nash equilibrium, because it's easy to see that in this case, the loser can always change his mind and switch his strategy from losing to winning. However, if the players just randomize their strategies and choose rock, paper, or scissors uniformly at random, it's easy to see that neither player has any incentive to defect. Okay, so some players, most games do not exhibit a pure Nash equilibrium, but at least one mixed equilibrium exists. And this gave rise to the computational question of how hard is it to actually find a Nash equilibrium given two n by n payoff matrices with, say, payoffs between -1 and 1. And this was one of the problems that started algorithmic game theory. It was proposed as sort of a complexity theoretic critique of economics, namely that we shouldn't base economic theories on the ability of solving intractable problems. And there's this famous saying that basically the point here is that the market, your laptop, we can always simulate decentralized computation, a market computation on a centralized machine. In some sense, the essence of this talk will be the reverse, that it need not necessarily be true that we can simulate any centralized computation by decentralized algorithm. So how hard is it to actually to solve this problem? It turns out to be extremely hard. I will not get into the details, but at least in the purely centralized or computational model, this problem turns out to be extremely hard, potentially requiring exponential running time in the size of the matrix n.
We don't have any reason to believe that it's really extremely
Well,
hard. There are like three other problems which are similar that hang on it. So we don't
Well, I think at this point we have so many evidence that support and contradict it that I think your intuition is.
was in a very similar state.
I see.
And,
Yeah. Fair enough.
What's
Fair-
the best statement?
So this problem is complete for some for p-pads, which is it's a class of total search problems, basically based on a parity argument, which is the best algorithms we know for solving this class are exponential. But as Avi says, it's not clear if this is the state.
Could be the polynomial surprising.
yeah.
It could be. We don't have proving any super polynomial lower bounds on p-pad is extremely interesting open problem. That we
What do you mean? But moving from polynomial low bounds
on-
that is different than
on p-pad, right? Did I mean so? Right. Sure. But I'm saying that as far as we know, we don't have any.
It's probably not NP-complete and it's thought to believe not to be in P.
Yeah, it's for example, it's in the intersection of P and of NP and co-NP, and the reason is that these are total search problems. But it's really not let me take this offline. I think so.
I will steal from you, you will automatically get back.
Oh, really? Oh, that's a bonus here. Okay, so yeah, so so whether you believe it or not, trust me that the evidence so far indicate that this problem is hard to compute, and this naturally led to the notion of a relaxed notion of epsilon approximate Nash equilibrium, in which intuitively speaking captures.
So this hardness result, the values themselves in the matrix, what if you restrict them to a very small set of values, say plus minus 1 or like a very small alphabet? Is it still hard or is
That's
I think there is
a good question. No, Noga and Shach, I think, isn't that about the support size? I'm not sure it has to do with.
about something that's
But
I
you
see.
also
The,
approximate equilibria.
I just believe the hardness is from the values being very,
no, I think it's.
high
I mean,
accuracy.
once we start speaking about approximate equilibrium, all these precision issues will vanish basically because. But so I think it's a more robust problem to consider. In fact, the hardness result, the PPET hardness result, the classical one of Goldberg et al., was for the approximate equilibrium problem with exponentially small precision. There was shown that even with polynomially, let me say something about the approximate.
If it's low rank, something low rank or low cost, I think it's Schreiman and Aron.
If it's sparse, that was if it's sparse, then it's.
Low one is still hard.
Yeah,
I
low rank,
think
I mean,
so.
you mean rank 1. Rank 1 is known to be.
Something of this sort.
Anyway,
Okay.
so-
One. Okay, I'm not familiar with this result. But in any case, this led to this more relaxed notion of an epsilon approximate Nash equilibrium, which intuitively captures a scenario of an approximately stable state in which neither player can gain more. Previously, we required that no player can gain anything by defecting. Currently, we require that no player can improve his utility by more than an additive factor of 1 over a million or very small value. So is the concept clear? So mu and sigma are mixed strategies form an epsilon Nash equilibrium if neither player can gain more than an epsilon additive factor. And I want to stress that beyond potentially making the computational problem more feasible, this notion is appealing also because it captures a much wider, richer set of desirable behaviors which are observed in practice. So, for example, it is well known that, I don't know, for the experts in the crowd, that the iterated prisoner's dilemma game, or there are many natural games that exhibit just one unique equilibrium, which is always to defect. But once you relax the notion to an approximate equilibrium, then you get many classes of natural behaviors like tit for tat or grim trigger, in which the player will cooperate until the opponent defects, and then he will punish him for the rest of the days. In any case, I just want to point out that this is not just a computational relaxation. This also seems more appealing for economists. So, so this is the notion that we'll focus on. And it turns out that, at least computationally speaking, the centralized model, this problem becomes, relaxing the problem to an approximate equilibrium makes the problem significantly easier. So you can solve it in quasi-polynomial time. And the main insight here is that any game with payoffs, bounded payoffs, has an epsilon approximate Nash equilibrium, which is supported on a very small set of pure strategies. Okay, and the proof is, I didn't give the proof, but the proof is very easy. So it's basically a concentration. So you take an exact Nash equilibrium, mu and sigma. If each player samples from it independently and uniformly, independently at random, each player samples log n over epsilon squared pure strategies from his own respective strategy profile, and you take the uniform distribution over these samples, it's just a matter of using standard Chernoff bound to show that this uniform distribution over those small subsampled pure strategy sets will form an epsilon Nash equilibrium. Okay, and this immediately gives rise to this algorithm, because then you need to, this was an existential fact, you actually need to enumerate all of them, so you just enumerate all possible sets of size log n from n, which takes exactly this time.
So this is for every epsilon?
Yeah. So in particular, that's a good question, because so I want to point out that the algorithm remains polylogarithmic even for epsilon, which is 1 over polylog n, and we'll focus on this regime.
I wouldn't say this is easy. This is the analog of exhaustive search. It's just there are less solutions.
I see. So you're not easy in the sense that,
You just say,
well,
I have less solutions to search, but I'm still searching overall.
Yeah, but it's just faster. The problem with epsilon is 1 over a million. It's just the polynomial instead of exponential. It's not a question about what the algorithm does. If it's stupid or wise, it's just about the running time. It's just faster.
I think in some sense there is, I'll say, give some indication that the problem is still hard in some sense. But yeah, I just want to, while I'm at it, I'll just say that so the best hardness result is for epsilon, which is 1 over poly n, like 1 over n to the 6th, in which case you get nothing here, right? So this remains.
There are like fixed parameter stability results.
I see. For what values of it?
You cannot expect a polynomial time algorithm.
I see. So
this is the content of. So there's a paper of Pagliasso and. I mean, this problem is related to finding log n clicks in a graph and the problem of putting VC dimension.
Are you talking about the welfare maximizing Nash equilibrium, or finding any?
I think.
I see.
So, okay, I have to.
Okay, let me, because there is. Okay, so. Yeah, so understand. So this is the state of the art, at least for general. For the general problem of finding an epsilon Nash equilibrium, and whether we can beat this algorithm and achieve actual polynomial time is one of the major open questions in the field. I think, and it's really not clear whether. So there are many evidences, supporting and discouraging this possibility of whether we can actually get polynomial time here. I will not get into this. I think the world record is a polynomial time algorithm that computes 0.339 Nash equilibrium. And by the way, Zev, so this is the only algorithm I'm aware of that does not use exhaustive. It does not rely on any support enumeration principle. So it's doing some gradient descent, and so at least there's some hope to. So it is true that if you restrict yourself to any support enumeration based algorithm, you cannot beat this. But this is, who knows? There might be.
So the question, because it's an additive error, don't you have to normalize things somehow?
Yeah,
So no.
Entries are between -1.
So throughout the entire talk, the entries are between -1 and 1, right? Yeah. Okay, so and kind of the race continues. So people mainly in the operational research communities keep searching for a polynomial time algorithm. But I want to make the point that it's not clear, what this problem actually models, right? Because it assumes, one could argue that it assumes in this unrealistic assumptions that the algorithm is fully centralized. It observes, there's some central authority that observes all of the players' payoffs. It's allowed to arbitrarily manipulate them and so forth. And this assumption is somewhat unrealistic. This was exactly the point of the works. This is what happens when economists dive into the picture. And the point of Mascolel's and Hart's work was that, player valuations are assumed to be private, and therefore decisions are assumed to be made on an individual basis. And therefore, it seems that the communication complexity model, or any model of distributed computing, is a much more suitable model for studying this question. And kind of the motivation or the supporting argument of these works was trying to understand the rate of convergence of decoupled or decentralized adaptive market dynamics. And where the holy grail is to have not just a centralized algorithm that computes Nash equilibrium fast, but a decentralized procedure that achieves this goal. Okay? And I want to point out that communication complexity, at least from a lower bound side, is a very robust model to study this question because it's completely oblivious to any bounded rationality assumptions of the players. It doesn't care whether the players are communicating directly or through a mediator, whether they're strategic or honest, if they're playing iterated best response or regret minimization. All it cares about is the number of bits that go through the channel. And in this sense, at least, it's a very compelling framework to, it's a very compelling type of statement.
Yeah, the question is what's the meaning of the consequence? Because they can finish in n squared bits, they can relay the whole information.
Right.
So it doesn't really
So let me, okay, that's why, okay, when we start talking about the implications of, we'll say something later about k-player games in which the size of the inputs are exponential in k. So I don't know if this is more convincing or not, but
it's not, this is unrealistic in itself. Probably they have implicit evaluation. So
I see.
right, I mean, in many.
I mean
that's
fair.
Might as well do exhaustive search, and that will be pointed out.
I see.
Another
Yeah.
time.
Sure. That.
Well, anyway.
Okay. So from now on, we'll focus on the communication problem where Alice observes, as in reality, she observes her own payoff matrix A. Bob observes his own payoff matrix B, and the matrix have values between -1 and 1. These are n by n payoff matrices, and the goal is to find any Nash equilibrium of the resulting game. And as obviously Avi points out, the trivial solution to this problem is Alice can always send her entire input matrix to Bob and finish with n squared bits. And I just want to stress that when we have n players, so when the parameter is the number of players, not the size of the game, then the analogy of the trivial protocol is exponential communication, not n squared, because when we have k players or n players, the size of the input matrix has to specify the valuation for each k tuple or n tuple of the valuation profile, and therefore the inputs are exponential. Okay, so I'll mention this, but we'll mainly focus on two-player games. And so what was known about this problem? So Hart and Mansour and previously Conitzer and Sandel proved that, well, if you want to find an exact mixed equilibrium or decide whether an exact pure equilibrium exists or not, then you cannot beat this trivial algorithm. And they proved it for the k-player version, but you can easily recover this result. But the point is that, and the question is, how about epsilon Nash equilibrium? And Hart and Mansour results completely breaks down when you talk about epsilon Nash equilibrium. So in fact, it relies on this encoding argument, which you can easily bypass. So it turns out the Hart instance of Hart and Mansour, which requires n squared bits for exact equilibrium, can be solved using a constant number of bits, so log 1 over epsilon or so, if you're willing to settle for an approximate equilibrium. So their proof is really it's like this half-page Jordan game or whatever, but it completely breaks down for approximate equilibrium. And let me try to convince you that there's something going on here, that there's reason why we don't understand what happens for the approximate case. So first of all, it turns out you can find a 0.75 Nash equilibrium with absolutely no communication at all. This might not impress you a lot, right? Because the payoffs are, given that the payoffs are between -1 and 1. But if Alice and Bob are willing to invest a polylogarithmic number of bits, they can already recover a 0.43 Nash equilibrium. That, well, something non-trivial is going under the hood here. It's not the problem is subtle in some sense. And what I view, at least, as the most compelling evidence for why the problem is interesting, or at least more interesting than the exact case, is that verifying a solution is very easy. So the non-deterministic communication complexity of this problem is polylogarithmic for any value epsilon, which is 1 over polylog n, right? Why is that? Because Merlin can always drop from the sky, and we already saw that there's always an epsilon Nash equilibrium which is supported on polylogarithmically many bits, right? So Merlin can drop from the sky, exhibit those sets to Alice and Bob, and now verifying that a given set of strategies form a Nash equilibrium, an approximate equilibrium, is something that can be done completely privately. I don't need Avi to check that a given pair of strategies is good for me if satisfies the equilibrium constraints for me, right? So Merlin comes, he writes down the support of the sets. The players simply check privately whether the uniform distribution over these supports form an epsilon approximate equilibrium. Okay, this is by no means the case for the exact equilibrium case. So this shows you that there's a conceptual difference between the exact problem and the approximate problem. And indeed, there were absolutely no lower bounds nor techniques for this problem, which was...
Why is it different? Non-deterministically?
But not quantum, only one direction.
Sorry? What's the...
Or maybe I got that.
The last statement is true also for exact Nash.
No, what? No. I'm saying that the non-deterministic of exact seems to be n. I mean, of course, if you have a proof that the non-deterministic is n, then this would imply that the deterministic is. But I'm saying that.
Writing the
So even, but even if I do not, right? So that's, you see, that's one of the other problems with the exact problem, right? That even writing just specify. But even if I do not require this, even then, it seems that that's.
No, but they can check. They know it somehow in their heads.
Right.
Check.
But yeah, so I'm not sure people have looked at it but at the non-deterministic of exact, but.
Well, the natural decision question is whether a given pure strategy is in the support of the optimal.
Right.
Well,
Sure.
what can you say?
So a natural decision problem is whether, let's say I give you an
Oh, you
I,
see.
which is a pure strategy, and ask whether it is in the optimal support of one.
Of one of the equilibrium, of any equilibrium. Sure. Okay, so for the approximate problem, no lower bounds nor techniques were known for any value of epsilon, even exponentially small. And when we thought about this problem, this made us come up with this central problem of this talk, which is the approximate fixed point of composition problem, which is a sort of a geometric two-party communication problem. And this is the problem we'll be focusing on. So in this problem, Alice is given the truth table of a function. So what you're going to see now is the reduction I'll present now is sort of, you can view it as a robust converse to Nash's theorem. So Nash showed that any Brouwer fixed point gives you a Nash equilibrium, corresponds to a Nash equilibrium. In this reduction, we'll see that any approximate Nash equilibrium can recover an approximate fixed point. Moreover, it will be in a distributed, in a two-party variant of this.
So that's what they do also in the...
Exactly, in the computational world.
Yeah.
Right, exactly. So this is but it relies on a somewhat different argument, but that's true. So, right, so, okay, let me not, yeah. Okay, so what is the problem? So Alice gets the truth table of a function mapping the n-dimensional solid cube to itself. And in communication complexity, the setup is discrete, so let us discretize the input space. So Alice's function maps the alpha grid of the n-dimensional solid cube to itself. But this function is not arbitrary, so this function is smooth. It's not too crazy in some sense. So it's a lambda 1 Lipschitz function, which means that in the L infinity sense, in the max norm sense, the distance between the any neighboring points, right? The distance of between their images is proportional to the distance between the original points. Okay.
Should we think of lambda 1 as constant?
Constant. Everything constant. Yeah.
Like constant sensitivity function.
Yep. Sure. Oh, you're viewing it in the combinatorial. Sure. Yep.
No, sensitivity is when you change one bit.
Yeah. So you rather not.
This is an infinity. It's not that one.
Well, I'm not sure what Avi means by
An
sensitivity,
infinity is
but
maximum. So you can change all the coordinates by its most.
All
yeah. But I want you to So it's important. So important that we're measuring this in L infinity norm. Why? We'll see this hopefully in the remainder of the talk. So Alice gets the truth table description of a smooth function from that n-dimensional cube to itself. And Bob gets a similar function. So he gets a smooth function, lambda 2 Lipschitz function, mapping the alpha grid of the n-dimensional cube to itself. Make sense? And what is their goal? Their goal is to find. So it's just I want to think of them as I want to think of the functions as truth tables, and we're in the communication complexity setting. So I want to represent everything by bits. We'll see that you can extend these functions to be continuous, but let's.
But alpha is also a constant.
Everything is a constant.
Depend on epsilon.
Great.
Alpha and lambda 1.
Great. So alpha, lambda 1, and lambda 2 should be thought of as constants throughout the talk. Okay, and what is the goal? So this defines the inputs of the two-party problem. The goal is to find an approximate fixed point of the composed function, which is obtained by concatenating the black arrows with the green arrows, right? So the black and green arrows specify the displacements of the function. Does it make sense? So Alice's function, I drew the arrows which specify the displacements. X is mapped to f of x, let's say, right? So in this language, what does it mean to find an approximate fixed point of the composed function? The composed function takes of the composed function g composed on f is obtained by concatenating these edges, right? F takes x to f of x, and then g takes f of x to g of f of x. Yeah. I'm just saying this is a figurative illustration. That's all I'm saying, because this figurative illustration will be easier to understand later. So does it make sense? Okay, so what's the approximate fixed point in this case? It's this one here, right? Because you can see that, so marginally to Alice or Bob, it doesn't appear as a fixed point, but it's an approximate fixed point. So does the problem make sense? So the first theorem we prove is that any two-party protocol, deterministic or randomized, that finds 1 over log squared and Nash equilibrium can recover an epsilon fixed point where the precision is proportional to the product of the Lipschitz constants times the granularity of the grid. And I won't elaborate on this, but this is the approximation factor you should expect, because this is, in some sense, the precision loss obtained by rounding an exact fixed point on the alpha grid. Okay, so I can say something about it. So such a point is always guaranteed to exist because Alice and Bob can marginally extend their functions to be completely continuous without increasing the Lipschitz constants. That's a well-known fact. By the way, non-trivial, but it holds. And then Brouwer's fixed point guarantees that the composed function always has an exact fixed point in the solid cube. And then you can always round it and suffer this precision loss, and this gives you an approximate fixed point.
Why are you thinking about functions that are Lipschitz?
We
still don't know that. Okay.
You still don't know that, but I'm saying that this theorem immediately pops up the parameters. I mean, you see that this is the precision of a fixed point you can obtain. Okay? So, again, so like I think Avishai says, so any function on a bounded set, any continuous function on a bounded set is always uniformly continuous, right? So it's in particular Lipschitz. But for this setting of the parameters, have discrete functions, so we want to be explicit about.
But
But
it sounds
because
actually
he wants to
continuous.
use this in the law now.
Sorry. So exactly. But let me. So let me. But let me prove this theorem and this reduction, and I think it will be clear. So this reduction can be viewed as a kind of a generalization, or it's in some sense inspired by. It's a distributed version of an idea that appeared in a completely different context in Schmeier's blog, and then in a more relevant context of the query complexity.
Doesn't it appear, for example, in the completeness theorem, and the decade earlier, almost Shichen and when they for two approximate to Nash.
They use this Sperner type reduction, right? Yeah, it's definitely. It's yeah. I see. Yeah, I'm saying no. Yeah. So showing that reducing Brouwer to Nash, that I agree. But the technical, let me describe the reduction, and you'll see what's. Okay, so let me give a sketch of an easier proof. Let's see why an exact Nash equilibrium gives you an exact Brouwer fixed point. You'll see the main ideas will already be here. So remember, Alice and Bob each have their inputs of the truth tables. They want to find an approximate fixed point. They want to find an exact fixed point of the composed function. And they want to do that by translating the problem into a Nash problem. So what they do is the following. So Alice and Bob construct the following two-player game G, whose actions are all the points in the n-dimensional alpha grid. So Alice gets to choose a black point in the alpha grid of the n-dimensional cube, and Bob gets to choose the green point. So the number of pure strategies here is exponential, right, in the dimension n, right, because we're allowing all the points. And whatever I'm going to say here is completely, the players are imaginating this. Everything is in their mind. There is no communication in this step. So now Alice defines her own payoff function. Everything is in her mind, right? So, and her payoff for any given points, x and y, Alice's payoff is proportional to minus the L2 norm between her point x, the black point, in the image of of her function f under Bob's action y. So the intuition is that Bob is choosing a point y, f is going to throw it somewhere else. Alice is trying to chase this point, right? Alice tries to match this point. This will minimize her loss, right? This will max. Does it make sense? And similarly, Bob.
Eventually, the one that x, y is a Nash equilibrium in the original game, that the solution.
I will show that. I'm describing a game that can be obtained using no communication, such that any exact Nash equilibrium in this game, if you have a too good to be true protocol that finds an exact Nash equilibrium, this protocol will produce you also an approximate fixed point of the composed function. Okay, so and similarly, Bob defines his own payoff function, so Bob is trying to chase Alice's point under his function g. And then the crucial thing is that defining these payoffs can be done completely privately, right? So Alice's payoff function only depends on her input f, right? That's important.
What is the answer? It's a grid or something?
The grid size, it's 1/1000. It's the grid granularity.
It's misleading because this is an n-dimensional box. It's not like the pair.
Right. Oh, sorry.
Very much like
Sorry,
the
I
pair
should.
matrix, but this is not the pair.
Sorry, this is the grid. This is alpha,
Yeah.
right? So each. Sorry, yeah. It was easier to draw. Okay, so this is the game, right? This step required no communication, right? So now suppose Alice and Bob have a too good to be true protocol pi that finds some Nash equilibrium mu sigma, right? The heart of the proof is showing that, at least in this case, this equilibrium must be pure, in fact. So why is that? So suppose Bob's equilibrium strategy is sigma in this equilibrium produced by the protocol. Right. What is Alice's payoff by playing any pure action x? Well, just by definition, it's the expectation over Bob's point y of the L2 norm between x and the image of Bob's point. So I claim that this function has a unique minimizer. There's one point that, what is it? It's just the expectation, right? It's the well-known principle that expectation always minimizes the variance. So it's, and in fact, this will hold convex function, right? So any convex function is minimized or maximized by the expectation. So I claim that Bob's unique best response is to play the expectation of f of y over Bob's strategy sigma. So I'm slightly cheating here, right? Because this point might not actually lie on the grid. This is where the approximation factor comes into play. But let's give me this leap of faith. So if you believe this point actually lies on the grid, Alice's best response is to choose this point. Okay? And a similar argument ensures that Bob's best response for any equilibrium strategy, sigma and mu, Bob's best response is always to choose the expectation of G over Bob's strategy. Make sense? This is why we use the L2 norm here, not L infinity. We could use any convex function, but it's okay. So if you believe this, then any Nash equilibrium of this particular game has to be pure. So we just saw that x always has to be the expectation of Bob's value, but it's pure, so it's just f of y. And Bob has to play the expected of g, but x is pure, so it's just g of x. And combining these two gives you that y star is an exact fixed point of the composed function. All right? So showing that the approximate argument is significantly more involved, but in particular, you can no longer expect that any approximate Nash equilibrium is pure, right? But what you can show is that any 1 over log squared n approximate Nash equilibrium, it's not pure, but it has some nice structures. So it's supported. So it's supported. Each equilibrium strategy is completely supported, encapsulated in a single cube, alpha cube of the grid. And that's intuitive, right? Because suppose Bob plays sigma. Alice wants to play this strategy, but she can't. It's not on the grid, right? She cannot match it. But if she plays, so it's intuitive that she'll try to play some strategies which are supported here. Because if she ever tries to play there is absolutely it doesn't make sense for Alice to choose a strategy which is far away. Right? She's trying to imitate this point as close as possible. So that's the intuition. And you can formalize this using the notion of well-supported Nash equilibrium, but
So why do you get log n?
so the log n is because
Because exponential, n was exponential in the little n.
No, I don't think that. So the reason is that remember, we had to, because we're using the L2 norm, we have to normalize the payoff by the dimension. Right? Oh, okay. So sorry. So that was.
Okay.
So what little n is the dimension? Little n is log of big N, right? So what I'm saying is, in order to get payoffs between minus and plus and minus 1, we have to normalize, and therefore any deviation, this argument that I just illustrated, that any approximate equilibrium has to lie. Every deviation is scaled by a factor of 1 over log n, where n is the log big N. Capital
N is equal to the little n, or n to the little n to the little n. So it's a right scale.
I'm saying that each payoff, the scale of the payoffs to begin with, is like Avi says, is 1 over log of capital N. So anything you can argue about this scale will be, the payoffs are on that scale anyway. So.
I understand. So once you have this game, then you lost log n.
Yeah. So that's what you can see all the losses. Everything. The highest possible gain in this game is 1 over log capital N. So the payoffs are between plus and minus log squared capital N.
And then L2 norm is needed.
So the L2 norm was required for the convexity argument, right? Basically for arguing that the best response is to choose the expectation. And now when you're not allowed to choose the actual expectation because it's not on the grid, so you're rounding it. And rounding it is basically, you're rounding it to the closest place. So all I want you to believe is that any 1 over log squared n, any approximate equilibrium of this game has to be of this form. These are the expectations, and everything is supported around those expectations. So you have 2 cubes, and okay? So I claim that if you recover those cubes, which the too good to be true protocol does by assumption, then I claim that this point, rounding the closest point in Bob's cube, forms a 2 lambda 1 lambda 2 fixed point of the composed function. It's a simple argument. Let me not prove it. Okay. So is everyone fine? So what we showed is that any 2-party protocol pi, deterministic or randomized, that finds 1 over log n squared Nash equilibrium in a game with capital N logs pure strategies can solve the approximate fixed point composition problem with this precision. Right? So, and in fact, okay, so now obviously the goal will be to try and lower bound the communication of this problem. We will not see, so let me first say, so for the sake of the lower bound, I want you to believe that the same reduction, exactly the same reduction, applies even if we allow F to map the n-dimensional cube to an m-dimension, so the intermediate space can be larger, and F can map the n-dimensional cube to an m-dimensional cube, where m you should think of as linear in m.
Polynomial.
The dimension m is 100n, is linear in it. Linear. But the number of the points is polynomial. And G maps back the m-dimensional space to the original space. So I claim that the same reduction exactly applies, except one thing, right? What happens? The number, okay, so in particular, the composed function still maps the n-dimensional cube to itself, right? The only thing that changes is that the number of strategies is now 1 over alpha to the m, right? Because now Alice will choose points in a much larger cube, but it's still polynomially related, like Avi says, right? So why am I considering this? It's completely unclear at this point, but all I claim is that it's sufficient to prove a lower bound for the slightly more general problem. This is the problem we study, where F maps the n-dimensional cube to a 100n-dimensional cube. This function is lambda 1 Lipschitz, and the same thing applies for Bob. So Bob maps back the m-dimensional cube to the n-dimensional cube. Okay, so I claim that proving a lower bound here will, if you're willing to suffer this loss in the exponent, then this is good enough. And okay, so this is the problem we're going to focus on. And our main result is that there are constant parameters, lambda 1, lambda 2, and alpha, and a linearly related dimension m, such that any deterministic protocols that finds not a lambda 1, lambda alpha fixed point, but a lambda 1, lambda 2 alpha over some absolute constant, this problem requires exponential communication. So unfortunately,
What do you mean exponential communication? The matrix is n by n.
no, exponentially little n.
I thought so what is the
Okay, this is the problem where, okay. But now I'm going to say what you want to hear. So I just want to claim that if we manage to get rid of this 123, then if the same lower bound holds without the 123, then I claim that this would imply that finding a 1 over polylog n Nash equilibrium requires some n to the small constant, n to the omega 1 communication. And we can also show, and this is a slightly more involved reduction, that finding a constant approximate Nash equilibrium in a k-player game would require essentially, as much as communication as it can. So 2 to the omega k over log k, where 2 to the k is the trivial upper bound. Right, so let's just see the first bullet. Why is the first bullet? Why would it follow?
So do you believe this? Do you believe that it's true that you can get rid of the
Yeah, I believe it's possible. Let me say it's less trivial than we thought, but let me.
But why does it matter?
First, okay, so the first thing I should say is that there is some qualitative.
Well, you don't get any corollary without the one, but
Not for the Nash. I mean, you cannot say. You cannot say anything about. I mean, maybe you can. I'm not sure, but at least for what we know is that you must get the. You must basically what it says is that you need to smoothen your lower bound. You have to make f and g smoother by a factor of 123. And lambda 1, lambda 2. So the product of lambda 1, lambda 2 is much larger than 123. It's like, I don't know, 2,000 or 1,000. And you should, so does it make sense? So the problem states that, so if you could make your functions smoother by this factor and still make the lower bound go through, then you would get that's one way to obtain to get rid of this factor.
You don't prove a lower bound on the communication complexity of Nash.
No, so that's,
This is open.
this is still, yeah.
Nothing is known. I mean, nothing
Nothing.
follows from this, like maybe
I don't think so. I mean,
the root law.
no, I mean, we're obviously still
asking,
trying to,
yeah.
no, we're obviously
Yeah.
trying to, no, but I mean, maybe it's possible, I'm not sure. I mean, once you start on your mindset is,
What's going wrong in the reduction? I mean, when it's 1, 2, 3.
so first of all, you should understand there is a qualitative difference because this is not necessarily a total search problem, right? You cannot guarantee that such a fixed point actually exists. So this problem, you could potentially hope to reduce it from something like disjointness or something. Turns out it's very unlikely, and you'll see why. But I'm saying there is a qualitative difference between finding a lambda 1, lambda 2 alpha and a lambda 1, lambda 2 alpha over 123.
Okay. Just
Okay, but why? The fact.
lambda 1, lambda 2 alpha is a search problem. It's a complete problem.
So this is a promise problem where the players are promised to have such a fixed point and they need to find it. Okay, and we'll see a class of hard functions which are guaranteed to have this fixed point, and we'll see that any deterministic protocol that recovers this fixed point must spend exponentially many bits. Okay, but
get rid of the constant,
then you get then it would be, I'm saying this problem is a total search problem, and in particular it would imply the Nash, a tight lower. So I guess, yeah, what surprises Avi, and I agree, there's surprising is that if you get rid of this constant, you get the best lower bounds essentially you could hope for. These are essentially tight lower bounds. But if you don't get rid of the constants, I don't know of any implication so far.
Do you have an intuitive explanation why the reduction we just presented doesn't work?
Oh, because you cannot hope to, I think the intuition is that you cannot hope for the reduction to produce that quality of a fixed point because it's simply not guaranteed to exist.
And if you know that F and G.
Oh, that's you see, the problem is that Brouwer's theorem guarantees that there is always fixed. Nash's theorem guarantees that there is always a mixed equilibrium,
Okay.
right? So, okay, maybe it will be clear when I describe the reduction, the proof of this theorem, which seems not true. So, yeah, so I completely agree. It should be possible to get rid of. There is one technical obstacle that I guess Ran will be the judge of that. We'll see how where this breaks down. Yeah.
As you said, this is already dependent on infinity norm, right?
Right.
So why do you take, is that the best choice, or what happens if you look at other norms?
That's a good point, and you'll see why you consider L. The reason why you consider L infinity comes from the technique.
You can prove something, but maybe there's other definitions that are not
Sure, but I think all of the definitions. Remind me this question in a second. So just to prove the first, so it's clear, right? So the first reduction says that finding that quality of a fixed point is that finding a approximate Nash equilibrium is at least as hard as that problem. if we knew that this requires exponential time, this would, because m and n are linear, or have a linear relationship, this would imply the n to the delta communication. And you can apply this. So the way we prove the k-party version is by a k-party number in hand variant, a multi-party variant of the fixed point problem. You can show that if you have a too good to be true two-party protocol, then if you have a too good to be
K has to be small.
No. I'm saying that if you have a too good to be true k-player, here's how we prove the k-player variant. If you have,
a number in hand or number in
oh, it's a number in hand problem. Yeah, because then, no, the point is that the natural economic scenario is number in hand, right? It's very weird that I only see Puya's valuations. But you could study the number in forehead problem. Okay, so let me spend the rest of the time, I don't know how much time I have, but like 10 minutes or on showing how we prove this theorem. And so, I mean, the intuition, right, is that if Alice has like a random function f and Bob has a random function g, neither of the players have any idea where the fixed point lies. Therefore, Alice might as well send the function. Of course, Alice does not have a random function. It's a very structured function. The geometry, you have to appreciate the geometry here. That's what makes everything here non-trivial. Okay, so Alice has a very structured function, smooth function, which could conceivably make the problem very easy to solve. Luckily, it was showed, this problem was studied in the easier query complexity model. So here's Papadimitriou and Vavasis proved this really beautiful result. And what they show, so they considered the query complexity of approximate fixed point. So in this case, there are no Alice and Bob, right? Where you're just given a black box description of a continuous, of a Lipschitz function h that maps the n-dimensional cube to itself. And the question is, how many queries do you need in order to discover an approximate fixed point of this function? And what they showed is that for any n, any dimension n, there exists a family of 72, they're very explicit about it, Lipschitz function, age, such that finding 0.01 fixed point of this family requires exponentially many queries in the deterministic communication model.
And so 72 is bigger than 1.
No.
It has to be. It has to be. Oh, it's a good point.
The
Why?
infinity is always between -1. This is most 1.
No, but the ratio. But the Lipschitz is a ratio. No, I want to say. So what happens if the Lipschitz constant is smaller than 1? That would be very easy to find. So one of the first statements in this paper, by the way, you shouldn't, I just want to stress that even deterministic query complexity of this problem is 60 pages. And the reason is the geometry. So, and this is what so what they show is basically they take a discrete random walk on the hypercube, purely discrete, a step function. And what they show is how to compile this walk completely in a continuous fashion. Basically, you see this path, right? So these arrows are the displacements of the function. X is mapped to f of x. And they show how to imitate this walk in a way that the unique fixed point of this function and all approximate fixed point lie basically in the point which corresponds to the end of this path. Okay, so now it's pretty intuitive, right? If you want to find even an approximate fixed point, you have to discover the end of the path. And if you ever try to take shortcuts in a random walk of exponential length, you'll be walking in the dark in no time, right? Because the mixing time is so fast. Does it make sense? So, and by the way, this intuition was formalized by Babichenko last year, who proved the analog for the randomized query complexity. Randomized communication complexity of this problem is hard. Okay, and our main result is that the communication complexity of approximate fixed point with these parameters is at least the deterministic query complexity of this problem. I guess to this audience it's not so surprising anymore, given the recent techniques. And of course, the techniques we use are lifting the query problems to a communication problem. And I don't know, I probably won't spend a lot of time because this audience is probably familiar with it. But So the idea of splitting is taking the input to the query problem, which is just a bit string of n bits, and splitting each input, each coordinate of the input, splitting it between Alice and Bob in some carefully chosen way. And this, in a way, and if the way of splitting the inputs is careful enough, it's hard enough, then the hope is that the communication complexity of the resulting distributed problem remains as hard as the query problem. So I'll go over this very quickly. So the problem is that, of course, the index, the gadget that determines how each input is being split between Alice and Bob, this gadget is extremely crucial to such a result. For example, if the gadget, if S is the AND function of n bits, and we split each bit using the AND gadget itself, then the resulting problem, what is the communication complexity of the resulting problem? 0, sure.
0.
Okay. Does it make sense? So if Alice and Bob get the deterministic query complexity of the AND function is n bits, right? You cannot avoid searching for, you'll have to search the entire input. But the deterministic communication complexity of the lifted problem, if you lift it using the AND gadget, is 0, like Avi says, because each player can just look if he has a 0 in any of his inputs. Okay, it's important. I want to stress the point that the gadget, it's not just a magic trick that you can take any problem and split it using any gadget and get whatever. The gadget has to prevent such manipulations. So what Raz and McKenzie showed is that basically there's a universal gadget problem remain as hard as it was for the query model, and that's the indexing gadget. So in the index gadget, Bob will receive a huge array of inputs, and the right input will be somewhere hidden inside this garbage pile of entries. So in Raz and McKenzie, Bob has an entry, a fresh array for each coordinate. We'll consider just one huge array. And this is not very surprising because we will require the size of this array to be much larger than n anyway. So it shouldn't be too surprising that we can just take all of those fresh arrays, stack them together, and get just one huge array. Okay, so what Raz and McKenzie proved, and what was generalized recently by Gus, Pitassi, and Watson, is that they proved the following simulation theorem, so to speak, that for any search problem, and it could be literally any object, it can be a partial problem, a total problem, a non-Boolean alphabet, anything you can think of, the deterministic communication complexity of the distributed of the problem S composed with the index gadget is at least the query complexity of this problem. Okay, and so the other direction here is clear, right? Because why? So I claim that the upper bound here always holds. You can just simulate any decision tree for S using just Alice will send her log n bit index. They will just simulate any. The highly non-trivial direction is proving the lower bound side, right? So the last thing I want to say is that probably we'll end here. So, okay, given that we agreed what is the index lifting, I want to ask you, what happens if S to be the approximate fixed point problem that Hirsch, Papadimitriou, and Vavasis considered? So this is just this is the description of the input to the query problem, right? It's just a collection of coordinates. Each coordinate has a displacement, has an arrow saying where F is mapped to. Make sense? So it's a non-Boolean alphabet, but it's a legitimate search problem. Okay? So what happens when you, so what's a coordinate here? A coordinate, again, it specifies the displacement of the input x. You know, there are exponentially all the inputs in the alpha grid of the n-dimensional cube. And I claim that this is the one simple observation of this basic observation here is that if you take each input and you decompose it using the index gadget, then you get exactly the approximate fixed point composition problem. Okay, so I'm claiming something very simple. If you view Alice and Bob's inputs as the truth table of functions, this maps the n-dimensional cube to the m-dimensional cube, and this one maps the m-dimensional cube to the n-dimensional cube. The index gadget encodes exactly the truth table of the composed function. Let me say this again. If Alice and Bob view their inputs as truth tables of Alice views the indexes as mapping, as a truth table mapping the n-dimensional to the m-dimensional cube, then the index gadget exactly encodes the truth table of the composed function, f composed, g composed on f. Right? There's nothing sophisticated here. It's just an observation. So great. So now we can apply the Raz-McKenzie theorem, right? Or not, right? So of course, the challenge is to carry out this decomposition in a way that respects the geometry of the problem, right? Raz and McKenzie never guaranteed anything geometric about the decomposition. We want the decomposition. So in Raz and McKenzie, decomposition will send each entry in F to a completely random location, right? That's the natural Hart distribution. That would result in a non-Lipschitz function, right? So the entire challenge here is carrying out, and this is basically, right? So does it make sense? So the hard challenge here is combining the combinatorics of the Raz-McKenzie theorem with the geometry of the proof.
So again, what do you want to show that?
What?
You want to build it in a way that the function is smooth.
Exactly. So you want to carry out, so we go into the Raz-McKenzie theorem, and we say that by increasing the dimension enough, we can get f and g to be sufficiently smooth, almost sufficient. So let me say this.
You are allowed to choose F and G. You are
Yeah. I mean, it's a deterministic communication lower bound. So what will we do? We'll
G is already smooth and is given by Hirsch, Papa, Dimitri, Babas, right?
Sure. Yeah. Right.
You want
Right.
to make F smooth.
Right.
The index.
Exactly. So, but okay. So exactly. But what needs to be observed here is that, right. So let me say it this way: if you make absolutely no restrictions